I'm Adam from RFOXiA from our real lab. Today we are answering why does a drone lose its GPS position fix in cities and forests, and what a GNSS module actually has to do to prevent that. Here is a fact the drone industry does not advertise. When your flight controller reports a GPS lock, it is not necessarily telling you where the drone is right now. It may be telling you where the drone was 3 seconds ago, or 5, or it may be extrapolating from the last known good fix using inertial data, hoping the real position hasn't drifted too far. The system looks stable, the position dot on your screen is moving, and the GNSS module is quietly not tracking anything. Let me explain how this happens. A GNSS receiver calculates position by measuring the time it takes for signals to arrive from multiple satellites simultaneously. To produce a three-dimensional fix, you need a minimum of 4 satellites with clear line-of-sight geometry. The word geometry matters here. It is not enough to have 4 satellites in view. They need to be spread across the sky at different angles so the receiver can triangulate without ambiguity. When satellites are clustered in one part of the sky, positional accuracy degrades significantly even if the signals themselves are strong. Now introduce an urban canyon. You are flying a drone between 2 buildings. The sky above you is a narrow strip. Satellites directly overhead are visible. Satellites at low elevation angles to the east and west are completely blocked by the building faces. Your effective sky view has been reduced from a hemisphere to a slot. The receiver still has signals, perhaps 4 or 5, but they are all coming from nearly the same direction. The geometry is poor. Dilution of precision, which engineers use to quantify this geometry problem, increases. The positional uncertainty grows, and in severe cases, the receiver loses fix entirely. There is a second failure mode that is more insidious than geometry loss: multipath. Building surfaces reflect GNSS signals. The receiver picks up not just the direct satellite signal, but also reflections that have bounced off glass facades, concrete walls, and metal structures. These reflected signals arrive slightly later than the direct signal because they have traveled a longer path. The receiver cannot always distinguish between the direct signal and the reflected copy. It averages them. The result is a position that is measurably consistently wrong, not drifting, not uncertain, just incorrect by a fixed offset. Your drone believes it is hovering at a specific coordinate. It is not. Forest canopy presents a different problem. The signal attenuation through wet leaves and dense vegetation can drop received signal strength by 10 to 15 decibels. That is enough to push weak satellite signals below the receiver's acquisition threshold. The number of tracked satellites decreases. If enough signals fall below threshold simultaneously, which happens during heavy rain or under dense old-growth canopy, the receiver loses fix. The third failure mode is interference. GNSS signals arrive at Earth's surface extraordinarily weak, around minus 130 decibels, reference to 1 milliwatt. That is a signal so faint that a poorly shielded DC motor, a misconfigured video transmitter, or a nearby 5G base station operating in adjacent spectrum can overwhelm it entirely. Single constellation receivers are particularly vulnerable because they have no redundancy. If the interference is broad enough to affect the GPS L1 band, the receiver goes blind. Now here is the critical detail that explains why most commercial drone modules fail in exactly these conditions. They track a single constellation, GPS only in most cases. The entire fix depends on satellites from one network at one set of frequencies. When the geometry is bad, when signals are attenuated, or when interference hits that frequency band, the receiver has no fallback. It was never designed to have one. Multi-constellation reception changes the geometry of the problem fundamentally. GPS operates at approximately 20,200 kilometers altitude. Galileo operates at approximately 23,222 kilometers. GLONASS operates at approximately 19,100 kilometers. BeiDou operates in a mixed orbit, including medium Earth orbit and geostationary satellites at various altitudes. These 4 systems are not synchronized. Their satellites are not co-located. At any given moment, they are distributed across different positions in the sky. When the urban canyon blocks the low-elevation GPS satellites to the east, there may be a Galileo satellite at high elevation to the north still visible. When L1 interference degrades GPS acquisition, GLONASS operates on different frequencies and may be unaffected. When the forest canopy attenuates signals from one cluster of satellites, satellites from another constellation at a different sky position may have a cleaner path through a gap in the canopy. Concurrent multi-constellation tracking does not eliminate the physics problems. Buildings still block signals, canopy still attenuates, interference still exists, but the receiver now has 15, 20, sometimes 25 satellites available across multiple orbital planes and multiple frequency bands simultaneously. The probability that enough of those satellites are visible from enough different angles to maintain a geometrically valid fix is dramatically higher than with any single constellation. The failure mode shifts from hard fix loss to graceful degradation. Accuracy decreases slightly when conditions are bad, but the fix survives, the position is real. This is why the first fix time matters as well. In a single constellation receiver, if the module loses fix during flight and must reacquire, it is searching through the available GPS satellite pool, typically around 31 operational satellites distributed across the sky. A multi-constellation receiver searching across GPS, Galileo, GLONASS, and Beidou combined has access to over 100 satellites. The probability of acquiring enough signals to re-establish a fix within 1 second is substantially higher. The drone does not have time. That is why single constellation receivers fail silently in exactly the environments where precision matters most. Now let me show you the hardware that addresses this directly. This is the Multinav Pro Plus built on the u-blox MIA M10Q. It tracks GPS, Galileo, GLONASS, and Beidou concurrently, not switching between them, tracking all four simultaneously. That is the architectural difference between a module that survives an urban canyon and one that loses fix in it. 1.5 meters of positional accuracy at 18 Hz. The accuracy means the reported position is close to the real position. The fix rate means it is close right now, not a second ago. For a drone in motion, both numbers matter equally. Neither is achievable on a single constellation receiver at this price point. The full multi-constellation system draws 25 to 30 milliamps. The module footprint is 26 by 22 millimeters. That is smaller than a postage stamp running 4 satellite networks simultaneously. Power and size constraints are the two most common reasons developers compromise on GNSS capability. This module removes both constraints. UART and I2C interfaces on a single board. Supply voltage accepts both 1.8 and 3.3 volts. That covers virtually every microcontroller and single board computer in common use, from ESP32 to Raspberry Pi to STM32. No level shifting required for the most common development targets. It connects and works. The driver library is fully open source, written in C, and implements the NMEA standard protocol, imported directly into Arduino IDE or any standard toolchain. There is no proprietary middleware layer, no locked API, no registration required to access the data your sensor is producing. The source is readable and modifiable. uCenter is the u-blox configuration and evaluation GUI. You can visualize satellite geometry, signal strength per constellation, positional accuracy estimates, and movement tracks in real time. For debugging fix loss in specific environments, or for validating that multi-constellation tracking is actually engaging, this is the tool that makes the module's behavior transparent. The use case list is the point. Drones, IoT deployments, wearables, automotive tracking, precision agriculture, research instrumentation. Every application on that list has encountered GPS fix loss in a constrained environment. Multi-constellation reception is not a feature for one specific use case. It is the correct architecture for any application that cannot afford to operate on stale coordinates. The fix rate matters equally. A receiver updating position at 1 Hz is telling the flight controller where the drone was 1 second ago. At the velocities a drone can travel, that latency introduces real positional error into every control loop calculation. An 18 Hz fix rate means the position data is never more than 55 milliseconds old. For precision hovering, for autonomous waypoint navigation, for any application where the drone needs to respond to its real position rather than its recent position, that difference is not academic.